Sucks, but
Alright, let's finish this. We're going to do.
everybody's over.
Have your attention, So, LR, and then LC circuits, and then we talked about Maxwell's equations, some review on Gauss and Ampere's laws, and then that would be it. Okay? So let's start with this one. I think I did it in one of the sections, but let's go over it together. Right? This one. The question is, how does the circuit behave long term? What is the current as a function of time? So, as time goes on, the current will go in the clockwise direction. And we're going to write down our modified circuit rule, the loop rule. The change from here to here is, from here to here, across the battery, it's E. And then you cross the resistor in the direction of current, it is minus IR. You cross the inductor in the direction of current, LDI dt, yes, okay? And then equal to 0. All right, so we're going to solve this equation. We solve by keeping di dt on one side and everything else on the other side. So we have the following. We have di dt is equal to, or L di dt is equal to E minus IR. And then we're going to multiply both sides by dt and divide by this. So we have L and then di divided by E minus IR is equal to dt. Then we need to integrate everything. Time from 0 to some final time t. And then this side, the current initially would start at 0, and then it would grow to some current t. This integral is natural log, but the chain rule gives you a minus 1 over r. Okay, so if you do that, you get minus L over r, natural log of the E minus IR, evaluated between 0 and r. On the right side, you just have t. Okay. To continue. So now, I'll multiply both sides by r over L with the minus sign. And here I'm going to evaluate. So when you evaluate, you have the natural log of, you substitute I, you get E minus IR. When you substitute 0, you get minus the natural log of just E. And when the difference between natural logs will give you this. On the right side, you have your minus r over L times t. Do the exponential on both sides. You have E minus IR is E minus R times t. Okay. And then our goal is to solve for I. So move this to this side, this to the other side. Factor and divide by r. So you get I E R times 1 minus E minus R over L. I skip this algebra step, but you can fit it in. So that's the current as a function of time. So what happens is, if you plot this, here's time, and here's current. This is E over R. At t 0, 1 minus e to the 0 is 1, so 1 minus 1 is 0, so you get 0. Expected. And the approach is done. Yeah.
If you had a capacitor on the circuit, you would have to current.
Yes. Yeah. We would consider it capacitor. So, yeah. So that's that. So here's what this is saying. At t equal to 0, the current is 0. So we want to know how do inductors behave. We know how capacitors behave, right? When the capacitor is N charged, it behaves like a wire. And then when it's fully charged, it's like an open switch. It doesn't allow any current through. How does an inductor behave? The opposite. So look at that. So at t equal to 0, the inductor doesn't allow any current in initially for that one moment. So at t equal to 0, we can redraw the circuit as follows. You have your battery, you have your resistor, and the inductor is just an open switch. Doesn't allow any current. As time goes on, this is t going to infinity. When the current is steady, the current approaches E over R. E over R is basically saying this: battery, resistor, and the inductor is just like a wire. What's the current in this circuit? E over R. Yeah. So as t goes to infinity, the inductor is like just a wire. At t equal to 0, when initially the inductor is like an open switch. So that's the intuition you should have. So the next is the, let's say our inductor now, there is a current running through it, and I would like to just consider an inductor and a resistor alone. Okay? So meaning this. Supposedly at that circuit, the current is flowing, you wait a really long time, so the current is steady and it's going, and then you attach a resistor to the inductor and just keep them along, meaning the following. Let's consider this circuit now. Here is the inductor, and we add the resistor. Here is the inductor, we add the resistor. So the current initially is going like this. We removed this part, right? This part, where the battery was the one to initially drive the current here. And then we remove it, and then just leave these two alone. And the question is, what is the current as a function of time? At t equal to 0, the current at t equal to 0 is just I naught. Okay? That's the current at t equal to 0. So what happens to the current as time goes on? It will decrease, because there is energy stored in the magnetic field in the inductor, and that energy will be consumed by the resistor. So the current should decrease as a function of time. And we'll see. Math will tell us it decreases. So let's go around our circuit. What's the change? I'm going in the direction of current. Direction of current, what's the change here?
L minus L d I dt.
Minus L d I dt. Yeah. And then here?
IR.
Minus IR. We're going in the direction of current. Equal to 0, right? So move this to the other side, so we get the I dt is equal to minus R over L times R, right? Minus R over L. Next is we'll divide. So I have di over I minus R over L times dt, and then we integrate. Integrate here from I initial, that's the initial current, to some final current, and here time initially 0, and then the later time is t. Okay, what's this integral here? Yeah, so when you get an ln, and then the difference between ln's will give you ln I over I naught. Good. So we can do that quick. And then this one is just minus r over L t. And so finally we solve for I. So I naught e to the minus r over L. So that's the current as a function. Graph it. Current. So it's initially I naught. This is the time. So it will just decrease. That's for an LR circuit, right? How about LC? That's the third and last one. You can also add an LRC. Every time you're solving a different equation. You can put a battery with a resistor, with a capacitor, and an inductor. So you can have all kinds of combinations. But we'll just do just the next one, which is just an L and a C. Okay. LC. Ready to go on with the LC? So LC works like this. You have a capacitor. Let's say our capacitor has charge. Initially, it's Q naught. Okay, that's the initial charge. We're going to have an open switch. And then we have our inductor. And then hooks up our inductor. There. Switch is open. What's the current? 0. No current. Good. We're going to close the switch and then we ask what happens. That's the question. So let's close the switch. What happens? Plus charges will start to go here and get to the minus charges. So the current will go this way, right? The current should start at 0 and then build up. So, but current will be in this direction. So, what's the relationship between the current and the charge on this plate? Relationship between the current and the charge on that plate. Where does the current come from? Flow of charge, right?
Yeah.
So the positive plate is losing positive charge. The positive charge of the positive plate is decreasing, and the current will go that way, right? Okay. So what's their relationship? I is what? V over R, huh? You see?
Charge over time?
Yeah, it is charge over time. So in terms of calculus, it's dq dt. Yeah. It is. It's dq. I'll put little q. It is dq dt. Yeah, that's actually the capital. So it's dq. So dq dt. But the direction of current is correct. But dq dt is minus, is negative. Why is it negative?
This is
Because
discharge.
it's decreasing. Yeah, it's discharging. So how do I fix that? How do I ensure that my current is actually will still be positive? Put a minus sign. Okay. That's where the minus sign comes. So the IDT will be what? What's the IDT? Second derivative, yeah. Now let's put it all together. We're going to start with the negative plate and go around. What's the change from here to here? Positive what? Q over C. The charge at the moment over C, yeah. The direction of current, what's the change here? Right? So we got this. The IDT is equal to 1 over LC times Q. Okay. But the IDT is the second derivative of Q with respect to time. So I'm going to replace the IDT by this, negative second. And the minus sign, let's put it on this side. That's the equation we need to solve. You have a function, you take its derivative twice, you get the same function back, right? You take derivative twice, you get the same function back, but with a minus sign and some constant. What's that function? Sine or a cosine? Yeah, it is the sine or the cosine. Up to us. It's, you can say cosine something t plus some phase shift. Okay. So the solution, the solution to this is q of t. And let's verify. I'm going to just give you the solution by uniqueness of the solutions to differential equations. If it fits the equation with the initial conditions, then it is the correct solution. So let's see if this makes sense. It's going to be the solution is going to be q naught times the cosine of 1 over LC square root times the time. And this 1 over the square root of LC is called omega. Let's see that if this makes sense. One is at t equal to 0, what's the charge? Q naught. So let's verify that. What's cosine of 0? 1. So you get Q naught, right? So that works. Secondly, the current should be dq dt, right? dq or negative dq dt, and it should be 0 at the beginning, right? At t equal to 0, the current should be 0. So let's see. So the current is minus dq dt. It would be, what's the derivative of this? Yeah, minus sign, so you get minus, and then there is a minus, so it becomes a plus, sign. So it'll be yeah, q naught over LC, right? Times the sine of 1 over LC times okay. So sine of t equal to 0, sine of 0 is 0. And if you plug it into the differential equation, if you do the second derivative of this is negative cosine, right? And this thing comes out twice. You will have 1 over L square root of LC times 1 over the square root of LC each time you derivative, so that's a 1 over LC. So that's the 1 over LC. The 1 over LC. The minus sign comes from differentiating twice. So what's going on? Well, what goes on is the charge as a function of time, it oscillates. Sometimes this plate is positive. At the beginning, here's what happens. This plate starts positive, and the charge starts to go. Eventually, the charge on either plate is going to be 0, and the current is going to be maximum current going through. But inductors, they don't like change. Once you get a current going, the current will keep going some more. So when you keep, if both plates are 0, and now you start adding plus charge to this one and removing plus charge from this one, this becomes the negative plate, this one becomes the positive plate. It switches, this becomes plus, this becomes minus. And the process repeats. And then it repeats. It's oscillating or alternating current. The current will change direction. It never stops. It will keep going. Of course, there is always some resistance. So eventually it will stop.
Wait.
Yeah. Yeah.
So the current will always be there?
Yeah.
Like in this circuit?
The current, sometimes it will be 0 for a moment, but yeah.
But it will like change
It
the
will
direction.
change directions, yes.
But for the RL one, it
Yeah.
will, the charge will gone, right? Because it is dissipated through
Yeah,
energy?
yes,
Yeah.
correct, yeah.
Oh, okay, I get it.
So this one there is charge, energy is lost, it's
Yeah.
dissipated in the
So the-
resistor. For this one, the energy is alternate. Sometimes it's stored in the capacitor as electric energy, and sometimes it's in the inductor as magnetic energy, like the maximum. So let's continue, and then we'll worry about the exam. Okay. So we will worry about the exact topics. So can I raise this thing? Raise this board up. Because I want to write. So Maxwell's equations is the next topic. So we're going to start here. So the two will not be combined together, so you have them separate.